We are continuing with the test review for the second test. We're now ready for problem 14. The instructions for problem 14 are: determine the intervals where the graph is concave upward and concave downward. Also find all inflection points. So we look at concavity, or concave up, concave down. The second derivative will tell us about concavity. And just like the first derivative, we're going to go get the second derivative and then find the critical points of the second derivative, which will be where the second derivative equals 0 or is undefined. And then based upon those critical points, we're going to do a sign chart, because the critical points will break up the graph into regions of concave up or concave down. And then we have to go for each region determine whether it's concave up or down. So let's just go ahead and do this. Don't think this is horribly difficult, because it's very similar to what we've been doing with the first derivative. In order to get the second derivative, you have to take the first derivative first. So 4x cubed minus 12x squared plus 7. Now to take the second derivative, 12x squared minus 24x. Now, let's get the critical points of the second derivative. What we do first, we set the second derivative equal to 0. And solve for x. I can factor out a 12x. Looks like the critical points are going to be when x is 0 and x is 2. Now there are no critical points where this second derivative is undefined. That's only going to happen if we have some kind of a fraction. So now I'm going to make a little graph here, break it up into regions. So 0 and 2 are my critical points. So there are 3 regions. So once again, what's going to happen is, in each of these regions, this function is going to be concave up or concave down. And it's not going to change within each region. So now our job is to simply go into these 3 regions and determine whether it's concave up or down. And the key is, with the second derivative, if the second derivative is positive, then that's a concave up. If the second derivative is negative, then that's concave down. So let's create our little sign chart here. So I have 3 regions. Pick a test point in each region. So in region 1, I'll choose -1. Region 2, I'll choose 1. Region 3, I'll choose 3. And now I'm going to determine, when I use each of these test points, I need to determine, I don't even care about the number, I care about the sign of the second derivative. So in factored form, here's my second derivative. So this should be pretty easy to determine. So I plug in -1 for x into my second derivative. This parenthesis is going to be a negative, because -1 minus -2 is -3. 12 times -1 is negative. 2 negatives multiplied together. I just determined that region 1 is positive. Actually, region 1 is going to be concave up. If I go to region 2, I plug in 1. If I plug in 1 here, the parentheses negative, and this one's positive, so it looks like region 2 is a negative region, which means it's going to be concave down. And finally, for the third region, I plug in 3, it's positive, positive. Region 3 is positive, back to concave up. So, the intervals where it's concave up, region 1 and 3, region 1 goes from negative infinity to 0. Then also, we have region 3, which is from 2 to infinity. Concave down would be here in region 2, which is from 0 to 2. Now an inflection point is where the second derivative is going to be 0. And the way we confirm it's an inflection point, if we look at our graph, if the concavity changes at the inflection point, then obviously, if the concavity changes signs at one of our critical points, then that critical point is an inflection point. So here, it goes from concave up to concave down. So you can imagine concave up is like this. And then all of a sudden, somehow it sort of becomes concave down. So it looks like have an inflection point when x is 0. And here, at this critical point 2, concave down, maybe it looks like this. And then all of a sudden it goes concave up. So an inflection point when x is 2. All right, so that was number 14. Number 15, the instructions are, use the second derivative test to find the maximums and minimums. Normally, to find maxes and minimums, we key off of finding the first derivative, and we can always do the first derivative chart. But there's another way to find maximum minimums, and that's you still find the critical points of the first derivative. But then instead of doing a sign chart, you can actually use the second derivative to determine max or min. So let's go ahead and start this problem, because you're going to notice the beginning of this problem is the same thing we've done before, but then at the end we do something different. So for 15, here's the function x to the 4th minus 2x squared plus 3. If we want to find the relative maximums and minimums, we have to take the first derivative. So it's 4x cubed minus 4x. Now later on, I'm going to actually use the second derivative. So let's take it now so we have it when we need it. Second derivative will be 12x squared minus 4. Now to get the critical points for the first derivative, we set the first derivative equal to 0. And actually I'm going to factor out a 4x here just to save time. Actually, I could get rid of this 4 just to make it even simpler. This is the difference of squares. So it looks like I have 3 critical points, 0, -1, and 1. I don't have any critical points that are undefined because, once again, there's no fraction here. So in the past, in previous problems, I could take these critical points and form a graph and break it up into regions and do all that kind of stuff. And that would be a way to figure out, are these points maxes or mins or neither? But there's a second way to do it. You can actually take each of these critical points and plug it in to the second derivative, because the sign of the second derivative, once again, I just wrote this, but I'm going to do it again just to clarify. When you look at the second derivative is positive. At that point, your graph is concave up, and what's concave up end up being? It's eventually going to have some kind of a minimum. So when I'm plugging in these critical points, I know these critical points are max, relative min, or maybe neither. So if I plug in x equals 0 and calculate the second derivative, if it's positive, I know it's a minimum. If it ends up being a negative number, which is concave down looks like this, that would be a maximum. So let's just do that. Let's take our first critical point from our first derivative, and let's plug it into the second derivative. The second derivative is 12x squared minus 4, so 12 times 0 squared minus 4. The second derivative, when x equals 0, is negative 4. It's a negative number, concave down, which means we now know negative 4 is a relative maximum. Let's calculate the second derivative when x is equal to negative 1. So 12 times negative 1 squared minus 4. This looks like 8. Since it's a positive number, it's concave up, which means when x is negative 1, we have a relative minimum. And then let's see what the second derivative is when x equals 1. 12 times 1 squared minus 4. Once again, so it looks like we have a relative maximum at x equals 0, and we have relative minimums at x equals negative 1 and 1. So you can see, especially if the second derivative is easy to get, like it is in this case, this is a pretty quick and simple way to determine whether the critical points of the first derivative are actually maximums or minimums. All right, let's see what's next. Oh, here's another one. They give us two of these. So 16, same problem. Use the second derivative test to find relative maximums and minimums. Same procedure. Let's go find. Now, actually, I'm going to rewrite this because I'm going to find the first derivative, but anytime you have a fraction inside of an exponent, you can break up the fraction. And this, I think, is going to make it maybe a little bit easier to do the derivative. I'm going to use the quotient rule. So you take whatever's in the bottom times the derivative of what's in the top minus the top times the derivative of what's in the bottom. Derivative of the bottom, chain rule says you bring a 2 out, and you subtract 1, leaves 1 as an exponent, and then you multiply it by the derivative of what's inside, which is just 1. And you take the whole thing over the bottom squared. If it started out being squared, if I square it again, it's going to be x plus 1 raised to the 4th power. Now I need to simplify. Sometimes simplifying is easy, sometimes it's hard, sometimes you can't really simplify. What I'm going to do first is I really like to have 3 terms, like this is a term because all these things are multiplied. This is a term, and down here, I notice in each of these I have parentheses with x plus 1 inside. So if I factor out of the top an x plus 1 parenthesis, so for this one I'm left with x plus 1 times 2x, and this one I'm left with 2x squared, all of that over x plus 1 to the 4th. Now you notice this is a factor up here, this parenthesis, and if I compare it with the bottom, I can cancel this, and I would have 3 of these in the bottom. And let's go ahead and multiply out these parentheses here, so the top becomes 2x squared plus 2x minus 2x squared. And you notice the 2x squared minus 2x squared cancel out. So by the time you're all done, it's actually not as messy as it could have been. Looks like the first derivative is 2x over x plus 1 quantity cubed. Now, I'm going to find the critical points for my first derivative, because these are the points where I potentially have a max or a min. Now I set it equal to 0. When I set the first derivative equal to 0 and solve for this, hopefully you can see this denominator doesn't come into play. I can multiply both sides by x plus 1 cubed. Because it's 0 over here, I just end up with. So there's a critical point. Now in this case, I do have a fraction. So I have to look at what values of x would cause the first derivative to be undefined. And actually it would be x equal to negative 1. So those are my 2 critical points. Now, normally, oftentimes I would do my charting here, but this one says use the second derivative test. So now, if this is my first derivative, let's go up here and see if we can do the second derivative. Hope it's not too messy. So you take the bottom times derivative of the top minus the top times derivative of the bottom, which chain rule once again, and all that is over the bottom squared. So this time x plus 1 cubed becomes x plus 1 to the 6th. Once again, just like I did before, I'm going to factor out, in this case, I can factor out x plus 1 squared. So I can hopefully simplify this a little bit. So in here I have 2 times x plus 1 minus 6x over x plus 1 to the 6th. 2 of these cancel with 2 of these. If If I multiply out I think I have this, which simplifies down to now the whole purpose of the second derivative is just to plug in my critical points and to see what I have. So let's do 0 first. So what happens when I plug in 0 into my second derivative equation? 2 minus 4 times 0, 0 plus 1 to the 4th. Looks like negative, oh, that's 0. 4 times 0 is 0, so it's 2 over 1. So, looks like second derivative at 0, x equals 0 is positive, which means it's concave up, which means potentially when x is 0 we have a minimum. Let's see what the second derivative shows when I plug in negative 1. So I would have 2 minus 4 times negative 1 over negative 1 plus 1. You can see the denominator, this is going to be 0. So this is undefined, which basically means when x is negative 1, it's not a max or a min. So it looks like all I have is a minimum at x equals 0. And that's the answer to the question. All right, a few more problems. Number 17, they actually give you an expression for the second derivative, and then they say determine intervals where it's concave up and down and find the inflection points. So we sort of did this similar kind of problem with the first derivative. So these kinds of problems aren't too bad because sometimes the hard part can be figuring out these derivatives. So here they just give us the second derivative. So it's x cubed times, in parentheses, x squared plus 2x minus 3. Now I think to find the critical points of the second derivative, I got that's equal to 0. So I'm going to see if this factors. I hope it does, this trinomial here. And I think it's actually going to be if you multiply them, it's doing this in my head, let's make sure. So x squared, 3x minus x is 2x, 3 times negative 1. Yeah, I think that's it. So what you do, we're going to now find the critical points of our second derivative. So we set the second derivative equal to 0. Solve for x. Since it's already factored, it's pretty simple. Solution is x equals 0, negative 3, and 1. So once again, these values of x are going to break up my graph into regions of concavity. Let's just do it as we talk about it. So I got 0, minus 3, and 1. Turns out I have 4 regions. Within each region, the concavity is not going to change. It's either up or down. My job now is just to go in and determine what each of the regions are. So I'll do my sign chart. 4 regions, pick a test point in each region. -4, -1. Have to be between 0 and 1, so I'll choose 1/2. And then greater than 1 is 2. And for each of those points, I'm going to plug each of these test points in for x and figure out the second derivative, although all I really care about is the sign. So let's look up here. When I plug in -4, well, let me write it down here to make it clear. Because you don't want to do all this work and then just mess up on this calculation. So I plug in -4, x cubed, when it's -4 is going to be negative. -4, this is negative, and negative. 3 negatives make a negative. Region 1 is negative, which means it's concave down. Remember, I say a negative person frowns. A frown is like concave down. I plug in -1 for x into my second derivative. Negative, positive, negative. Multiply these out, you get a positive. Region 2 is positive, which is concave up. Now if I go plug in 1/2 in for x, positive, positive, negative. Region 3 is negative. Now if I plug in 2 for x into my second derivative, positive, positive, positive. So it looks like I have 2 concave down regions and 2 concave up regions. So concave up is going to be from -3 to 0 and from 1 to infinity. Concave down, -infinity to -3, and then 0 to 1. Now they also ask about inflection points. So once again, inflection points are where the concavity changes, as long as we have a nice continuous graph. So we go from negative to positive at -3. So -3. Then we went from positive to negative at 0, so 0 must be an inflection point, and then from negative to positive at 1. So let's look at 3 inflection points. All right, let me stop here now. So that's a lot of stuff with second derivative. Next, I'm going to do problems 18 and 19. I'm going to skip 20, and we're going to look at those functions and try and answer all the questions. So let's stop for now, and I'll pick up with the next video.